we are now in segment 4 of module 3. We have already seen a median algorithm based on sampling. We just saw how the algorithm works, but it is also reasonably clear that it is a linear time algorithm. What is not clear is why it is correct and how to analyze it. And that is going to be the plan for today. We are going to focus on the analysis of the correctness of this median algorithm, and we will be using Chebyshev's inequality. In particular, we are going to prove the following claim, that the algorithm fails with probability at most n to the minus 1 by 4. Okay. So, we already alluded to this claim. We are going to see how this is proved. And if you recall, Chebyshev's inequality requires you to know the expectation and the variance of the random variable. So, with these two pieces of information, you will be able to bound random variables that show up in the analysis. Okay. So, I will first recall the median problem, the algorithm, and some of the details there. Okay. So, of course, you have a set S arbitrarily ordered, and you need to find the median. That is the median problem. And let us recall the algorithm, and keep in mind that there are 3 major objects in this algorithm that interplay. Okay. There is the set S, which is the or the array S, if you will. It has the elements from which you need to find the median. That is the input set. Okay. And then the first thing that happens is you sample a multiset R. So, that is the second object. Okay. You have a multiset R, and it is of size n to the 3/4. These are elements chosen uniformly and independently at random from the set S. Okay. This is the sample. And the third object, well, before we go to the third object, what we do is we take this second object R, we sort it, and we pick out 2 elements D and U from this array. And our intuition is that D should be should be less than the median, but close to the median. It should not be too far from the median. Similarly, U should be greater than the median, but again close to the median. So, these are this is the intuition based on which the algorithm works. Of course, in our analysis today, we will be proving this intuition formally. And now comes the third object. So, based on these 2 elements D and U, you go back to set S, and you pick out all those elements that are in S that lie within the range D and U. Okay. That is the third object C. So, these 3 objects interplay quite a bit, and how these 3 objects interplay is very important. It is crucial to understanding how to analyze this algorithm. Okay. So, what is the intuition here? This third object, remember, D is to the left of the median, that is our hope, U is to the right of the median. So, when you take the when we are trying to understand the analysis, sometimes we look at S, but we look at it in the sorted view. Okay. The sorted view is not available to the algorithm. Remember, the analysis is one thing, the algorithm is another thing. Okay. The algorithm works on an unsorted list, but the analysis, for understanding how the algorithm works, you can view the sorted array and play with it. Okay. And that is what we are doing. So, in this sorted array, what you do is you can superimpose the set the array C, and remember, array C is something that we actually sort in the algorithm as well. And in this array C, what we do is well, the D, the smallest element in this array, we hope is less than the median in S, and U we hope is to the right of the median. So, this sorted set spans the median. So, it must encompass the median, but it should not be too large. It should be something like n to the 3/4. So, which means that because it spans the median, you can spot the median of S within the array C. Okay. This is the intuition that I hope you already have. Any questions on how this algorithm works? Any issues at all? Because that is understanding this algorithm is absolutely imperative to understanding the analysis. Okay. So, here is the 3 objects. Okay. Now, what are the recall that we we had some, we hoped some good things will happen. What was the first good thing that we hoped would happen? The D, the element D is to the left of the median. Okay. And let us ask ourselves, okay, how does that happen? If you think about it, where is the right event should occur right even when you sample the elements R. Okay. What is this element D? You go back to the fact that you first sampled this set of elements, this multi set of elements R, you sorted it, found the median, you walked left square root of n steps, and then you found the median. And from here, that ended up being the leftmost element in C, and that has to fall in this left region of S. Okay. Similarly, the other good thing that must happen is your U, this is a symmetric good event. U should be from the right part of the array S. Okay. And the third good thing you want is that the set C should not be too large, it should be no more than some 4 times n to the 3/4. Okay. And here is an important principle. So, there are these good events that you want, and you want to make sure that these good events happen with high probability. Okay. But often that is hard to prove. So, what do? We focus on the corresponding bad events, because those are often easier to bound. Okay. So, let us take these good events and convert them into the appropriate bad events. Okay. So, what is the bad event? So, the good event was that D falls on the left side, the bad event is that the D falls on the right side. Okay. That is one bad event. I am going to call that bad event number 1. Okay. I am going to denote that by a 1 enclosed within a circle. And of course, the mirror image is also easy to see. The other bad event is that the U falls on the left side. U should rightfully fall on the right side, to the right of the median, but falling on the left side is the bad event. Okay. And you want the C to be less than 4 times n to the power 3/4. The bad event is just the opposite. We will understand the third bad event more carefully and more slowly later on. Okay. But hopefully, the first 2 events, the corresponding bad events are easy to visualize in what is going on. Okay. So, let us formally write down the bad events, because now what we have here is a pictorial representation. This D over here, this D falling on the right side is the first bad event. Let us try to write it out formally, and let us make sure we understand how this works. And so, for this we first define a random variable y1. Okay. Y1 is simply all those elements in R. Remember, R, capital R is the set of elements that we sampled. Okay. So, original elements that we sampled, out of which we are picking out all the elements that are less than or equal to the median. M here represents the median, and we are asking how large is that set. Okay. And this is the this is the random variable y1, the cardinality of the set of elements in R that are less than or equal to the median. And the bad situation is when this y1 is less than this quantity. Okay. So, this will need this will require us to understand exactly why that is the case. Okay. So, y1, let us go back to this picture. Y1 is all those elements that are less than the median. So, y1 is you are counting the elements in this R. Okay. Please pay attention to this part. You are counting the elements in R, okay, but those elements that are falling to the left of the median. Okay. Yes. All right. So, let's see what so now why is that a bad situation. So, and in particular we are asking the particular bad event is when that quantity is less than half n to the 3/4 minus square root of n. Okay. So, let us see why that is the case. Can somewhere what I would suggest that you do is that you stare at this picture a little bit and convince yourself that this bad event is actually captured by this formal statement. Okay. So, what happens if the number of elements sampled from this region to the left is less than n to the 3/4. So, this by the way as okay. So, I think there is a small one more typo here, this has to, this median element has to be n to the 3/4 divided by 2. Okay. So, this median element here, let me correct that over here, small. So, this whole thing is of length n to the 3/4. So, this element is actually not n to the 3/4, it is by 2. Okay. So, apologies for that typo. So, here also we have that, okay, and it is minus square root of n, and this is divided by 2 plus square root of n. Okay. Now, what is y1? y1 is all those elements from R that are falling in this range on the left side. Okay. If this y1 is too few, where will D fall? In other words, if y1, those elements that are from the left of the median are just a small set of elements over here, where will D fall? So this is the intuition here. When this y1 is too small, when it is particularly lesser than this quantity, okay, it is just going to occupy a small part on the left of R, which means that this D will fall in this region. Okay.
Why that specific quantity, sir?
The specific quantity y1 or
no, that how does it come less than n to the power 3/4/2 minus n? Why y1 less than that?
Okay. So, we are trying to capture a bad event, right. The bad event is that D falls in this region, okay, and now we have to formally capture that bad event, and we want to capture it in such a way that we can apply Chebyshev's inequality. Okay. We want to define this random variable y1, which can for which we can find the expectation and variance, right, and be able to ensure that we can say that y1 will be small only with small probability. Okay. That is the bad event. When y1 is too small, the D falls in the bad region.
But the D will still be left of the median.
No, when the y1 is small, what happens? Think about it. What is y1? y1 is the count of the elements in R that are sampled from the left side. Okay. If that is a very small part of this set R, okay, D is positioned over here. If the elements corresponding to y1 are coming from this small set inside R, that will naturally push D to the right of the median. So, what is the precise definition here? You have defined y1 and you want that to be less than half n to the 3/4 minus square root of n. What does that mean? When y1 is less than this quantity, all the elements that were sampled left of median are only occupying the portion to the left of D. Okay. They are only occupying portion to the left of D, which means the dth element is clearly based on a position within R. So, you are finding the middle element and you are walking back square root of n steps. Okay. So, dth position D's position is fixed, but all the elements that correspond to y 1 are to the left, which means it, if you think about it, D will be pushed into the bad region. Okay. This is important, make sure you understand this, because this is how the analysis, a lot of setting up the variables to work out the analysis is captured in this step. Okay. Shall we proceed? If you want, I can give a minute to stare, for you to stare at this picture. That is a very good point. Thanks for pointing that out. So, Bharat's recommendation is that just think of the extreme situation where y 1 is simply all is equal to 0, basically means that no element was sampled at all from this region. So, even the smallest element is over here, which means that D is also going to be in this part. So, that is an extreme situation. It is not like the procedure magically knows what the median is and keeps the D at that point, right. The algorithm is just running without knowledge of what the median is, right. There is no magic about this. So, it is a proper algorithm, it's just, you are just sampling elements. So, you do not know where D lies really, I mean where the median lies, right. Okay. Okay. So, let us move on. So, this is the formal way to represent the bad event. Okay. If the first event is captured this way, the second event is going to be a mirror image. Okay. Here it is going to be another variable y 2, where you are looking for all the elements greater than or equal to median in the sampled set R, and you are asking how will that, the bad event would be that cardinality of that set, that is y 2, is fewer than n to the 3/4 by 2 minus square root of n. This is too small. Okay. This is just a mirror image, so not too tricky. And the third one, I am going to defer the details till later, but we will maintain, we will call it 3. So, we have listed the 3 bad events and we have given them names 1, 2 and 3. Okay. 1 and 2 are essentially the same. So, we are only going to bound 1 and the same bound will hold for 2 as well. Okay. What we are going to do is apply a union bound. This is a very important thing, simple but extremely useful. If you have a few bad things that can go wrong, in this case there are 3 bad things that can happen, and if you can ensure that each one of those bad things happens with very small probability, okay, then the probability that any one of those bad things happens is just at most the sum of the individual probabilities. This is just coming from inclusion exclusion principle and throwing away terms that we do not. So, okay, so let us look at this first bad event, okay, and recall that this is how we formally defined it. So, y 1 is the cardinality of this set, and the bad case is when it is too small. Okay. So, how do we bound this? So, remember we carefully define this random variable, so we can apply Chebyshev's, which means that we need to be able to find the expectation and the variance. Okay. So, we want to break y 1 into smaller pieces. What is y 1 is basically the count of the set of elements that are less than or equal to the median. Okay. So, go back to the sampling algorithm. Okay. You are sampling elements into this set R, xi equal to 1 if the ith sample is less than or equal to the median. So, remember this is, you have this less than or equal to here, right, that is what is defining your set which gives you whose cardinality is y 1. Okay. So, now what you do is you basically just define, you break y 1 into individual xi's, xi equal to 1 if the ith sample is at most the median value, 0 otherwise. Okay. Which simply means, so now the nice thing is xi is very easy to work with, because expectation of xi is nothing but a half, I mean close to a half. If you look at the textbook, they are very careful and precise about computing the median. I am being a little slack here, because it depends on how you define the median. Is it the middle element? If it is odd, you have a middle element. If it's even, you do not have exactly a middle element, so you have to look at the left of the middle position, what not. We are ignoring that and saying, look, the expectation of xi is a half approximately, close enough. Okay. And when you have the xi's, you can very easily compute the y 1. Y 1 is simply the summation of the xi's. which means now you can compute the expectation on the y1, because again linearity of expectation. And so, the expectation of y1 is n to the 3/4. Why? Because y1 the set R has cardinality n to the 3/4, okay? And each time you sample, the expected contribution towards y1 is a half, right. So, that is n to the 3/4 times a half, that is expectation. Of course, that is only half the story, you need the other half, the variance as well. Okay. Again, it is easy to compute the variance for the individual xi's. It is p times 1 minus p, if you recall, this is just a Bernoulli random variable. And again the p's and the 1 minus p's are roughly a half. Okay. So, the variance is roughly a fourth. Okay. And this is where independence helps, and I recall somebody saying, why did we sample with why not sample without without replacement. Okay. If you do it with replacement, you get independence, and so now you can compute the variance of y1 simply by summing the individual variances. Okay. So, remember the individual variances are a quarter. So, sum over all I, and remember there are I is running from 1 to n to the 3/4. So, you get n to the 3/4 times 1. Okay. So, we have the two pieces, the expectation and the variance. So, let us proceed from here. Let us go back to stating the bad event. Probability of the first bad event, if you recall, is that y1 is less than n to the 3/4 by 2 minus square root of n. Okay. But what is n to the 3/4 divided by 2? That is nothing but the expectation of y1. Okay. So, that is what, and what I am going to do now is rearrange the terms just a little bit. So, let us make sure we get a picture of what is going on. Often it is important, while working with these notations, we can lose track of the intuition as to what is going on. What is this asking? So, let us say we have this y1, this is the, let us say, the expectation of y1, and this is expectation of y1 minus square root of n, and we are asking what is the probability, and y1 has some distribution. We are asking what is this probability. This is the tail bound, right. We are asking what is the probability that y1 is going to be less than this quantity. Okay. And if you recall, though, Chebyshev's had bounds on both sides. So, it is not just this part, it also has this part. Okay. So, we are going to make life simple for us. We are going to convert this equality into a less than or equal to, and just bound both of them together. Okay. This is only adding probability to a bad event, and that is and if the upper bound still is within what we care about, then we are fine, right. So, this probability, how are we going to capture this? Basically, you are looking at this y1 minus the expectation of y1, and how do you fall in these two extremes? When the absolute value of this quantity exceeds the square root of n, then you are falling into either this region or this region. That is what is captured in this event. Okay. And this form is now exactly the way we want for applying Chernoff bounds. Okay. The probability of a random variable minus absolute value of a random variable minus its expectation exceeding some quantity square root of n, in this case, is at most the variance of y1 divided by the square of this quantity, right. So, if it was a here, it will be a squared here, right. So, it is square root of n here, so it is n over here, and if you work it out, variance of y1 is n to the 3/4 divided by 4 divided by n, it works out to 1/4 times n to the minus 1/4. Okay. This is one of some 3 different bad events, right, and it is contributing 1/4 of n to the minus 1/4. So, if you plug it into the union bound, there will be other. So, for example, this is the first bad event. You can do the exact same thing and argue the same thing for probability of the second bad event as well. That is also going to be less than or equal to n to the minus 1/4 divided by 4. Okay. And then what we are going to do now is we are going to show that the third event is going to be less than or equal to n to the 3 by 4 sorry minus 1 by 4 divided by 2. When you add up these 4 probabilities, one here and one here, it adds up to n to the minus 1 by 4, and that is where we completed our analysis. Okay. So that is what I am stating here, probability of the first bad event is equal to the second bad event. So, we are going to skip the second bad event. Okay. Now, we are looking at the third bad event. Okay. We need to be again a bit careful about how to approach this bad event. Okay. This is the bad event that this C, this third object in our algorithm, C is too large. Okay. In particular, we do not want it to be larger than 4 times n to the 3/4. Okay. Okay. So, let us say the bad event occurs. Okay. You can which means now your C is cardinality is more than 4 times n to the 3/4. So, then you can look at the bottom 2 times n to the 3/4 and the top 2 times n to the 3/4, and they are going to be disjoint, right, because it is the overall width is more than 4 times n to the 3/4. Okay. So, you are going to notice that one of few bad things will happen. In this case, if you notice, this top 2 n to the 3/4 elements in C are all greater than the median. The other possibility is that, but if you go back here, this bottom set is actually spanning going across the median. Okay. But at least one of them is fully to the right, fully on one side of the median. The other thing that could happen is both of them could be, one could be fully to the left and one could be fully to the right. This is also a possibility. The top 2 n to the 3/4 elements in C are greater than the median, the bottom elements, this bottom red portion is lesser than the median. The third possibility is that the right part overlaps, but the left part, the bottom 2 n to the 3/4 elements in C are less than the median. So, there are these 3 possibilities, but the best way to capture it is at least one of these two things will happen if the bad event happens. What is either the bottom part is completely to the left, the top part is completely to the right. Okay. So, basically the third event can be broken into 2 smaller bad events, okay, and these are again symmetric bad events. So, what we will do is we will just focus on one of them. Okay. If we show that and just to be clear, this is a bad event, but if this bad event occurs, it does not necessarily mean that the third bad event occurs. Okay. What this means is that it is the other way around. If the third bad event occurs, then at least one of these 2 bad events occurs. These smaller bad events occur. So, what we are going to do is really, if you were to look at it from a Venn diagram's point of view, let us say that this is the third bad event. Okay. So, if you what we can say is that if the we cannot say that if this were to happen, that implies 3, that we cannot say, but what we can say is if 3 were to occur, then one of these 2 occurs. So, this what we are really doing is we are taking a larger event. This is either this or this. This larger event is the OR of these 2 events, and what we are going to do is bound this larger event. Okay. And for that, what we are going to do is focus on the 2 separately and just focus on the first of these 2 bad events. They might be. So, let us see, not clear, right. So, both can happen and neither can happen. It's a little bit more complicated. So, let us not worry about that, because it is I think both can also happen or neither can also happen. Okay. These are all possibilities here. But let us just focus on this one bad event. Basically what we are focusing is that the top 2 n to the 3/4 elements in C are greater than the median. Okay. Okay. So, how will this happen? So, basically what is the rightmost element in this C? That is this element u, and what is happening is that element u is, what is the intuition here? The element u is occurring too far away from the median element. Okay. This portion is greater than 2 n to the 3/4. That is why this red portion, which is of size 2 n to the 3/4, is fully to the right of the median. Okay. So, now for this to have occurred, actually the problem started way back when we sampled in R. So, that is why we are going back to R. So, this is our u over here in R, this is the original sample, and somehow this u is, where is it falling in the sorted set R? It is falling at some position greater than 2 n to the 3/4 away from the median element. Okay. How would that happen? Again, it is a slightly counterintuitive way we are going to see how it is going to happen. How does u get pushed so much to the right? You look at all those elements to the rightmost portion of this set R. That is basically this portion, that is where is u? It's in the middle, half n to the 3/4. Sorry, this yeah, minus square root of n. This is correct because you are looking at these elements over here to the right. Okay, all of these, where should they have fallen? Where should these samples have come from? They should have all been contained within the top n to the n half minus 2 n to the 3/4, that is this portion. All of these elements should have been contained over here. That's how this u can get pushed to the right. Okay. I will let you stare at this picture for just a second. Okay. Why is this happening? U gets pushed to the right. It's more than 2 n to the 3/4 from the median. How is this happening? If you look at the sample set R and you look at the top portion, top half n to the 3/4 minus square root of n samples, all of them are drawn from this region. So, that is how u gets pushed so much to the right. Okay. So, now we can write out this bad event. Okay. So, now for that we are going to define this random variable x. It is the number of samples in this region, in this top n by 2 minus 2 n to the 3/4. Okay. It is the number of samples in R among the top n to the samples in R, but drawn from the top n by 2 minus 2 n to the 3/4 elements in S. Okay. So, now again you define a random variable, you break it into its components. So, xi is 1 if the ith sample is meeting the requirement of x, otherwise it is 0. So, this part should be obvious to you. Our capital X is simply summation of the individual xi's. So, your expectation of x can is simply the summation of the individual expectations, but here we need to be careful. What is the expectation of the xi? It is the probability that a sample will fall in the top n by 2 minus this 2 n to the 3/4 region, right. And that, what is the probability? It is n by 2 minus 2 n to the 3/4 divided by n. Okay. And if you work it out, you get this quantity n to the 3/4 by 2 minus 2 square root of n. Okay. Now, the variance similarly can be computed. So, you have the individual probabilities, and what we are doing is any times you have p times 1 minus p, and p value is less than 1, it's going to be at most a fourth. Okay. So, variance is going to be the summation of n to the 3/4 terms of the form p times 1 minus p. So, it works out to be 1/4 times n to the 3/4. Okay. These you can verify. Okay. So, simply now we apply Chebyshev's inequality, probability that, okay. So, what is the bad event? that this set of elements that we sampled from the top n to the this n top n to the half n by 2 minus 2 n to the 3/4 is greater than this quantity n to the 3/4, and that is greater than this quantity this n to the 3/4 by 2 minus square root of n. And now set this up carefully, because now you have this event x greater than this quantity. You want the expectation is n to the 3/4. So, if you look at this n to the 3/4 by 2 minus 2 square root of n. So, I am just going to subtract a minus square root of n and add a square root of n. So, I get it of this form. So, that I can write it as probability of x minus e of x greater than square root of n, and that is less than or equal to, now I again do the same trick of not just bounding the left tail, but also the right tail, okay. And that is going to be x minus probability of the absolute value of x minus e of x greater than square root of n, okay. And this is now exactly the form that we want. So, we can apply Chebyshev's inequality. It is nothing but the variance of x divided by n, and it works out to be n to the minus 1 by 4 the whole divided by 4. Okay. All of the bad events had the same type of probability. So, the first bad event had the same probability, second bad event by symmetry had the same probability, upper bound on the probabilities rather. The third bad event was broken into two pieces, and one of them has this probability n to the minus 1 by 4 divided by 4, which means that the other mirror image will also have the same upper bound. So, all the bad events, when you add them up, there are 4 of them. If you consider the third one broken into 2, there are 4 bad events, each of the same n to the minus 1 by 4 divided by 4. So, that is what I am showing over here. So, you have these two mirror symmetric bad events for corresponding to 3. So, you put all of them together, you get the upper bound on the probability of bad events is at most n to the minus 1 by 4, and this is exactly what we wanted. So, with that we can conclude. We basically I hope you got an appreciation for how Chebyshev's was applied in this context. We are able to, as you rightfully pointed out, it is just defining the right variables, setting it up the right way, so that you can connect your intuition with the formal analysis. Okay. And one reason we do this is intuition is often great, but intuition can be also deceptive. Okay. So, when I started teaching probability in computing, I thought that the previous median algorithm would also work with high probability. That was my intuition, and I was proven wrong, and I actually was able to prove myself wrong by saying, look, you can actually not prove that with high probability. You need this algorithm to prove this high probability bound on the median, on finding the median. Okay. So, the intuition is great to get you started, but often intuition can be misleading. So, you do need to learn how to analyze your algorithms more carefully. Okay. So, that is hopefully you are getting an appreciation for that. So, with that we will conclude. Next segment we will actually look at Chernoff bounds, which is a little bit more powerful than Chebyshev's, but in some sense restricted. Okay. So, that is it. Thank you.